Good afternoon, everybody. My name is Marjon Umbay, and this is a report on analysis and design of integrated circuits, naming the title of Power Analysis for Integrated Circuits. Part 1. Power Consumption in CMOS Circuits. In CMOS circuits, this composed of two transistors. Namely, the first one is PMOS transistor. A negative voltage on a gate turns the device on, while the NMOS, a positive voltage, turns the device on. In history, the solid-state transistor was invented in 1947 by Brattain, Bardeen, and Shockley. Replaced the vacuum tube due to its smaller size and lower power consumption and faster speed. Transistor triggered a revolution in the electronic industry. Modern microchip uses MOSFETs, which consists of NMOS negative and PMOS positive transistor. NMOS is doped with phosphorus or arsenic, while PMOS is doped with boron. Combining NMOS and PMOS in a circuit called as CMOS provides lower power dissipation and better noise immunity. Complementary metal oxide semiconductor or CMOS. CMOS circuit uses both N-type and P-type MOSFET or metal oxide semiconductor field effect transistor in complementary manner. N-type MOSFET or NMOS is used to pull the output down to the ground or logical zero, while PMOS type MOSFET is used to pull the output up to supply voltage logical 1. This complementary arrangement significantly reduces the power consumption, especially in idle state. This is the positively supply voltage or VDD, stands for drain. This is the negative supply voltage for FETs, called VSS, or stands for source. This is the source, this is the drain, and this is the voltage in, and this is the voltage out. This is a PMOS transistor, and this is the NMOS transistor, overall composing a CMOS circuit. In a CMOS. First one is dynamic. Refers to the power consumed by the circuit when it is performing useful work during the active mode. While P static, the power loss due to leakage current that flows through transistor when the circuit is inactive. Again, when the circuit is inactive. To calculate it, you need to add the static, P static, and P dynamic to get the P total. There are types of power consumption in CMOS. First one, as you can see in a tree below, in the diagram below, under the dynamic power, there is switching power and a short circuit power. And under the static power, there is a leakage power. Part 2. Dynamic Power Analysis. Dynamic power analysis arises from the charging and discharging of capacitance within a CMOS circuit. It is directly proportional to the switching activity of the circuit, meaning the frequency of which node transitions between logic gates. The sources focus primarily on dynamic power estimation techniques. power analysis. There are two case sources of dynamic power dissipation: capacitive charging / discharging or switching. Every time a node in a circuit transition from low to high logic level, the associated capacitance need to be charged by drawing current from power supply. Conversely, during a high to low transition, the capacitance discharging, just dissipating the energy. This is the figure of dynamic or capacitive charging / discharging or switching. The first figure here, the charging path and discharging path of the capacitive load in CMOS circuit. The first figure here. This is the charging and this is the discharging. The next one is a short circuit current. In CMOS circuits, there's a brief period during transition when both the NMOS and PMOS transistors in an inverter are momentarily on, creating a direct path between the power VDD and the ground GND. This results in a short circuit current contributing to dynamic power. And here is the figure of short circuit path in a CMOS circuit. Dynamic power analysis. Factor influencing the dynamic power. Load. This is the four factors influencing the dynamic power. The first one is load capacitance or C load. The larger the load capacitance, requires more charge to be transferred during transition, leading to higher dynamic power. C load includes contribution from the gate capacitance of subsequent stages, interconnect capacitance, and diffusion capacitance of driving transistors. Next one is the supply voltage. Dynamic power is proportional to the square of the supply voltage. Reducing the VDD is very effective way to lower the dynamic power. Switching frequency. The higher the switching frequency means more transition per seconds, directly increasing the dynamic power. Switching activity. The activity factor represents the average fraction of clock cycle which a node transition. It captures the statistical behavior of signal. On getting the dynamic power. First one is switching power. The power consumed when charging and discharging load capacitance during switching. It is influenced by the clock frequency, dynamic capacitance, and supply voltage and switching activity factor. To calculate the P switch, you just need to multiply all of these: switching activity factor, clock frequency, dynamic capacitance, and supply voltage. Then, let's go ahead to short circuit power. Short circuit power, the power dissipated due to a direct path current between the supply rails and both PMOS and NMOS transistor conducting simultaneously during switching. To calculate it, you need a P signal. You need a signal rise / fault time or fault time, peak short circuit current, and supply voltage. You just need to multiply all of that to get the P short. Then, to calculate the P dynamic, you just need to add P switch and P surge short. Part 3. Leakage static power analysis. Leakage or static power analysis. Static power is consumed when the circuit is in a steady state with no switching activity happen. In ideal CMOS circuits, static power should theoretically be zero. as no direct path exists between power supply and the ground in a steady state. However, practical CMOS circuit exhibits small leakage currents. Leakage or static power analysis. Key sources of static power dissipation in CMOS circuits. Threshold leakage. When the gate voltage of a MOS transistor is below the threshold voltage, a small current still flows due to the diffusion of carriers through the channel. This sub-threshold leakage increases exponentially as the transistor size shrinks. Gate leakage. Leakage current also flows through the gate oxide due to tunneling effects. Junction leakage. Leakage current also exists across the reverse bias PN junction within the transistor structure. And here is the formula in calculating the static power. It is simple. Just multiply the supply voltage and the leakage current. Static power, the power due to leakage current when switches is idle. P static. To calculate the overall static power, you need to add the subthreshold, the P gate, and the P junction leakage. Leakage static power analysis. Factor influencing static power. The first one is technology node. As technology scales down, leakage currents become more significant due to thinner gate oxide, swallower junction, and reduced threshold voltage. Temperature. Leakage current increases with temperature. Transistor sizing. Larger transistors generally have higher leakage current. Design techniques. Techniques like power gating and sleeve transistor can be used to minimize circuit static power by disconnecting the parts of the circuit from the power supply when not in use. Going to have an example scenario part 1 of power discrepancy calculation to calculate the overall power discrepancy of an CMOS circuit. This is just a simulation. So let's start. To calculate the switching power, we need the formula of it, which is switching activity, clock frequency, load capacitance, and supply voltage. Then substituting it to formula from these values, then calculating the product step by step. And after that, multiplying it to 6.25, which resulted to 312.5 microwatts. And to the next scenario, part 2, we just need to calculate the short circuit power, which we will have the formula of P surge, rise and fall time, multiplied by supply voltage, multiplied by peak short circuit current. Then, substituting the value inside the formula, calculating it, resulting to the 2.5 microwatts. Then after that, calculate the total dynamic power, which as we review from the back of our lesson, we just need to add the P switch and the P short circuit to calculate the P dynamic. So we just need to add the 312.5 microwatts plus 2.5 microwatts, resulting to 315 microwatts dynamic power. Before we calculate the dynamic power, let's proceed to calculating the static power or leakage power. To calculate the static power, we just need the formula V times I, leakage current. As you can see here, the leakage current multiplied by supply voltage would result for 2.5 nanowatts. From the previous topic, this is a summation of both P threshold, P gate, and P junction leakage. To calculate again the static power, you just need to add the P threshold, P gate, and P junction to get the P static. So, per P threshold, you just need the VDD or supply voltage multiplied by P threshold or the leakage of P threshold, VDD multiplied by P gate, VDD multiplied by P junction, and add all of it to get the P static. And the resulting is 2.5 nanowatts. And for the last part of scenario, we just need to sum the dynamic power and static power, substituting the value of 315 microwatts and 2.5 nanowatt would result of 2.5 nanowatt and overall of 315 microwatts, which is very minuscule. From the calculation, the result might minuscule, but when it is integrated in very large scale system where multiple CMOS is needed, it might result to a larger power dissipation. So let's see how to optimize the power of that. Here is the power optimization techniques. The first one is reduce the supply voltage. This method has a quadratic effect on power reduction. However, negatively impacts circuit performance and is not generally recommended unless switching to power saving mode is necessary. Next one is dynamic frequency scaling. This technique includes adjusting the clock frequency for specific application based on their performance profile. It can lead to energy saving but might increase the execution time and the risk application corruption if deadlines are missed. Third one is multiple supply voltage. This approach uses lower supply voltage on non-critical computational elements. It can achieve significant power reduction but necessitates careful power and floor planning due to the requirement of multiple power grid structure. The next one is clock gating or clock tree. Given the significant power consumption of clock trees in advanced microchip, gating the clock can reduce the clock power. Balancing the reduction in clock switching with capacitive load estimates is crucial for optimizing power consumption. Challenges can arise from suboptimal placement of gating logic, leading to larger clock network and increased power consumption. Downsizing gates. Gates is directly proportional to parasitic capacitance. Selectively, downsizing gates can reduce dynamic and leakage energy dissipation but may increase speed delay. This highlights the trade-off between operating speed and power reduction. Part 3. Interconnect power reduction. A significant portion of dynamic power consumption stems from interconnection capacitances. Optimizing the interconnect design, such as using a larger wire spacing and minimizing routing length for high power interconnect, can reduce the power consumption. Clock network optimization. The size of the clock network affects the power consumption. Optimizing register placement during cell placement can decrease the clock net wavelength. However, in high-density circuit, this approach might increase the routing congestion and adversely affect the signal net wire length. Net ordering and wire space optimization. The goal of this technique is to reduce the capacitance of the most active nodes. This is achieved by arranging adjacent signals to minimize the cross capacitance of high switching activity signals. Part 4. Activity analysis. Switching activity analysis is a valuable tool for power optimization. Understanding where and when the circuit exhibit the lowest and highest toggle rates help in selecting the most effective power-saving approach. Critical design blocks with high power consumption can be identified for targeted optimization. Transistor sizing. Similar to gate downsizing, minimizing careful transistor sizing can reduce the dynamic power by minimizing transistor capacitance. This strategy often involves trade-off with performance, necessitating logic or architectural speed-up techniques to compensate. Minimizing switching activity. Reducing the unnecessary switching activity of logic in architectural level is crucial for power optimization. And thank you, and this is my report. Thank you, Doc Marial.